forces between masses force depends only on the masses and relative positions. Now, if you've got a mass here and a mass here, and yeah, the other thing I guess we better say right now, could have waited, but force is of attraction. There's no repulsion as there is with magnets. Okay? So, we've got two masses here. Different masses, doesn't matter. Okay? And they exert a force of attraction here that we could measure. Kind of hard to measure in the lab, but we do have apparatus that allows us to do that for lead balls of about this size. Unfortunately, we can't do it because it's windy in here. We can't turn off the air. Okay, now we take this mass and we bring a second mass of identical mass and put it together with this one, right? What should that do to the force? If we double this mass, it's like bringing another mass identical to it to the same position. And that second mass is going to have the same force of attraction to whatever this mass is that the first one did, right? So it should be pretty clear that we've doubled the force, right? Okay? Well, you can extend that to saying, okay, if this mass is fixed, then the force has to be proportional to this mass, directly proportional. If this mass increases by some factor, the force increases by the same factor. Okay? Well, we don't have to keep this mass constant. We could also double this one, right? If we double both masses, what happens? We're going to fourple. We're going to quadruple. I love that word, fourple. One of my students invented that 30 years ago. He's wanting to say, I asked the question, Steve, or the guy's name was Steve. He's an accountant now, smart guy though. Not that accountants aren't smart. He was smart enough to do just about anything. He's a real good guy too. And he's back there. I say, okay, what happens to the force? And he said, it fourples. Couldn't think of quadruples, right? So that stuck. So that's my homage to Steve. Okay, so we've got these masses. Okay, so what it comes down to then is the force is going to be proportional to the product of the two masses. Okay, if I double this one and triple this one, what do I get? I get 6 times the force, right? Okay? You think that through, but it works, and I don't want to belabor it too much. So the force if the masses are M1 and M2, then the force is proportional to the product M1, M2. If you don't know the symbol for proportionality, it's because that's also hard to teach, so nobody ever does. Review it. Proportionality. I'm serious. You cannot understand formulas, which you love so much as engineers, without understanding proportionality. And the fact that you've gotten this far in your education and don't even understand the symbol for proportionality, despite the fact that I drew it rather badly, you should still recognize it. I started seeing it in 8th grade. Okay? Because that's back when we didn't bother with the fact that most people aren't going to understand it. We taught the people who would understand it what it is. Okay? If y'all haven't been thinking about that since age 12, fix it. Got it?
So how does it actually look?
Huh?
What does it actually look like?
Look it up. I'm not going to tell you. You can see I've inspired your curiosity. I'm not going to spoon feed you. That's what you've had all your life. Okay? Okay. It's, that's kind of distorted, but it's still recognizable. Okay. I think it's recognizable. Okay. So anyhow, our force is proportional to M1, M2, right? And it's an inverse square force. If the separation is R, then the inverse square property here, I'm going to draw a better one. It's still not great. These two things here ought to be parallel. But it's proportional to M1, M2 over R squared. That's what inverse square proportionality means, as anyone who'd even been through Khan Academy would understand. Okay? And I'm not denigrating Khan Academy. I think it's wonderful. Got it? Okay.